I will start presenting a little bit myself. So I'm Marta Pala, I work for Robotics, and unfortunately, Cecile could not be here. We already know why, and she sends her apologize for not being here because she always loves to be at the ERF. I will be more or less like leading this session and the next one. And well, I think it's good we just start, and I hope that everything goes well. So this first workshop is about Horizon 2020 projects, and we have the two different calls. So we will go through the different calls, and all our presenters will have a presentation on their new projects that the Commission has been funded. The first one is in application in robotics core technologies, and these ones were mainly in here, and they were given. And oops, yeah. So these were research and innovation actions. So there were two main on boosting promotions and applications. And they were selected for different projects, which I'm going to give the microphone to the first of our guests. So, all yours. And here is this.
Okay, thank you, Marta. Thank you, everyone. Okay, so this is a presentation about the project IM that I'm coordinating. This works, yeah. So this is the first slide of the presentation. So IM stands for Impact Aware Manipulation, and I think the best way to represent what I mean with Impact Aware Manipulation is with an example, and especially also to explain what the logo is about. This logo of the project shows a box. So we are in the context of logistics. We want to manipulate objects, parcels, objects that you can find in warehouses, and we want to do it with robots. So in the logo you see sort of a sketches of two hands grabbing a box, but we want to speed up manipulation. So we actually want to make contact with the objects at non-zero speed. So as person will do. So the question that we are essentially tackling is how can we have robots grabbing objects, pushing objects, tossing objects reliably, and use this to speed up manipulation activities in the logistic sectors, logistic domain. To tackle this problem, we have a consortium of 8 partners, 3 universities, 1 research center, and 4 companies. So we have TUE, Eindhoven University of Technology, that I represent, PFL with the Aude Billard as a PI, TUM with Samia Dadin, CNRS, actually the lab in Lirme in Montpellier with Abder Kedar. Algorix is a company in Sweden that is dedicated to dynamic simulations, software. Franca Mica, robot manufacturer. We want to have also hardware support during the project. Smart Robotics is a system integrator, so they develop robotics application in the context of logistics, and they are actually the system integrator of Vanderlande, which is the world leader in parcel handling in warehouses and airport. So a very large company that is located in the Netherlands. Okay, so so the motivation and why we want to do this, well, this is essentially known by anyone. E-commerce is growing, there's labor shortage. We definitely need to have this kind of activities, moving objects from one conveyor belt to another, from one box to another. But yeah, there are not enough people to do this job, and plus this job is not the most exciting. If you do 8 hours a day, picking objects from one box and putting in another. So that's not indeed the most rewarding and the kind of job. So the question is how to speed up and how to make it fast, indeed. And so what we propose is to do something different than before. There has been a lot of research done in vision, perception. There has been a lot of work done in designing grippers, but we are trying to tackle this with a different approach, and this approach is really using dynamic contact tasks. And so really making contact, like as I was explaining, at contact speed. So in order to do this, we have to essentially change all things in the whole pipeline. So we have to have models, so you have to make the robot aware of impacts, so we need models of impact, so that's validating impact models. We have to learn and plan things knowing that there are going to be impacts, so rapid velocity changes at the moment of contact. So how do we deal with that? We also have now, there has been a lot of research on collision, prevention or collision detection, but here we actually want to make collision. So we have to distinguish between intentional and non-intentional collision. And also we have then to develop a whole control framework in order to put things together. And this whole thing will then create this framework that we call in the IM. So what is the approach? Well, the approach is basically really looking at models that allow for discontinuity in the velocity due to impacts, creating an open database where we actually use a mock-up system and like an OptiTrack system to record these motions and make it publicly available to further validate these impact models for robotics. And also explore limits. So if we take a robot like the Franca Panda and we impact, so when will it break? So things like this, we really want to explore what are the limits. And we, of course, we want to incorporate these all condition models in the sensing, planning, and learning pipeline. So what is the impact of the project? Well, of course, if we can achieve this, the expected speed up is about 10% in the cycle time. So this is great for a company like Van der Lande that developed these automated systems for logistics. And of course, like I said, we relieve people from really dumb or kind of repetitive jobs. And for European robotics, this is also a how to say, indeed trigger the attention to the fact that we can change the way that a robot manipulate objects, including impact, instead of sort of slowing down every time you have to make contact with an object. With this, I would like to stop my presentation. Thank you for your attention.
Thank you, the organizer, for having invited me to present this combat project, which aims at designing and test a new class of robot that we call the combats, that will be used to physically couple people to help children in learning new motor skills. The consortium involves myself, Domenico Formica, as coordinator at Università Campus Biomedico di Roma, and we involve 3 other universities with expertise ranging from human robotics and wearable exoskeleton design and musicology, and 3 companies with expertise in machine learning, AR, VR, serious game design, and industrial grade exoskeleton design. So let me spend like a few seconds explaining the rationale behind our project, which comes from literature in motor neuroscience. Experiments have shown that when you try to accomplish a learning task, even a simple task like following a dot on a screen, and you are interacting with a robotic manipulator, if you put 2 people doing the same task and they are virtually coupled through a virtual mechanical impedance that couple the two robots, well, the performance in the tracking task improves, and improves both for the less skilled person and for the more skilled person. So we thought about bringing this knowledge to the real world, so using the same concept for real life application and learning task. The project is built around the design of 4 enabling technology for robotics. The first one will be the design of new robotic haptic device that will be designed purposefully to help people to physically connect among them in the form of end effector devices, which will be designed by the group of Professor Bourdet at Imperial College, and wearable exoskeleton, which will be designed at Scuola Superiore Sant'Anna by the group led by Nicola Vitiello, and UVO, which is a startup company of the same university. Then we'll design what we call a bidirectional user interface, which will provide feedback to the user using AR-based serial game designed by a Serbia-based software house, which is called AR VR Tech. And by ourselves at Campus Biomedico, we will use wearable technology for gathering data from the subject and provide information to the platform to readapt. And we will design both wearable garments, instrumented garments, and instrumented objects. Then we will have IBM, which will deal with developing machine learning algorithms that will process all the data come from the subject, try to identify the mental and emotional status of the subject, and try to readapt the behavior of the platform according to each specific status of the subject. And finally, together with Imperial College, we will try to synthesize a new controller, which is neuro-inspired in the sense that we will try to understand how the human brain behaves when it's physically coupled with another person, and try to synthesize a robot controller which will serve as robotic trainer for our user. This technology will be applied to education, and in particular to teaching children how to handwrite in primary school, and to how to play music for beginner musician. As I said, the whole working framework of the whole project is based on this neuroscience approach on physical communication among subjects. The impact, the expected impact of our project will be basically related to develop and test new robots, which we call the combots, capable of physically coupling different user in learning tasks. Hopefully we will strengthen the user robotics and technology supporting robotics to this new field of education 4.0. And finally, we will be able to probably, hopefully, build new businesses in this new field and boost the deployment of this new technology in real-life scenarios. I stop here.
So, test. So, hello everyone, my name is Cosmin Daria. I'm from Frankfurt CMA Hamburg, and I'm here to present the CCLEAR project. CCLEAR stands for Search, Identification, and Collection of Marine Litter Using Autonomous Robots. Okay, our partners are TU Delft, who is coordinating this whole project. Frankfurt CMA is doing the technical coordination and also the system integration. Then we have Subsea Tech from France, who is in charge of the hardware and enhancing their waterborne robotics for our project, together with TU Munich, which is in charge for the collection system of the litter. Then we have University of Dubrovnik, Croatia, who's in charge of the control of the aerial robotics, together with the University of Cluj-Napoca, Romania, which is in charge for 3D mapping of the litter and also for the exploitation plan. And last but not least, we have our end users, Dunea from Dubrovnik and Hamburg Port Authority, who design our case studies. Okay, our ambition is actually to create the first solution for collecting marine litter using autonomous robots. We aim to do that at 3 levels or stages. First, we would like to gather the data required for mapping this litter and do the identification of the debris so that we recognize what is waste, what is sea life. Then we would like to do the collection, the proper collection, and of course the remapping, because in the water column we expect that the waste will not stand still, of course. And last but not least, we would like to have the high-level control from shore, in which we have the command of an authorized operator, and in our vision, we would like to have an end user who can monitor the whole application or the whole pipeline using a web application, web app. Okay, our approach is depicted in this picture. We will use waterborne aerial robotics. Starting now from up to bottom, we'll have an offshore deployed USV, who will be our powerhouse, the robot that will handle the computational workload, which will be permanently connected to the shore, and also to the aerial and underwater robotics. In the lower level, I don't know if I can, we will have a collection UUV and an UAV, an aerial robotic, that will gather the data needed for designing or creating the 3D litter map. And later we have the collection UV, who will be obviously in charge, together with the USV, for collecting the actual litter. And we will add in the loop another observation UUV for remapping, as we talked before. Oh, sorry. So, first of all, I would like to say for the impact side that we are a heterogeneous group who are coming from very different backgrounds and trying to match or to combine academic research, applied science, and do a business plan. In that sense, we expect to strengthen the excellence of European robotics with various algorithms for detection using deep learning, advanced control techniques for collaborative control, and also grasping robotics. Then we would like to apply this knowledge into this overall system who should solve an immediate problem and hence boost the possibility, have the possibility of using robotics in a new and promising area such as ports cleaning and tourism revival scenarios. Then we would like to measure our performance, and if we reach our objectives, then we can consider that this project will be opening a new market for robotics, and hence this outcome can be further developed through a spin-off or startup through a business plan. And last but not least, we would like to lower the deployment barriers for such a system, and we would like to prove that the system is scalable with reasonable complexity and infrastructure, and hence basically revolutionize the world by solving intelligently one of its biggest current problems, namely marine waste. Yeah, that's clear. Thank you very much, and I am willing to answer more questions at the poster, and looking forward for talking with you.
Okay, so my name is Aleš Ude, and I'm standing here to present the Reconcycle project. Reconcycle is an acronym for self-reconfiguration of a robotic work cell for the recycling of electronic waste. So first, what was the motivation for our project? So standard methodologies in electro-recycling is called crush and separate. This means that basically the products that come into the recycling plant are first basically crushed into parts, then they are processed using some physiochemical chemical processes, and this way we can then extract usable parts out of them. And but before before this can be done, actually some parts that are dangerous needs to be removed from the product, so like batteries and so on. And this currently is done in electrocycling manually. So this is, of course, a major inconvenience and make electrocycling difficult. So why this is more difficult than, for example, classical manufacturing processes is visible from these photos here. So unlike in classical manufacturing, where you can assume that all parts are good, parts that you get into the electrorecycling much more come in different states, and you need to deal with this with your robot. So to do this project, we have partners with appropriate competences. So the coordinator is my group at Jožef Stefan Institute in Slovenia. And we are basically bringing into the project the concept of reconfigurable work cell design. So it's not just about the programming robots, but we also need to prepare the workspace so that it is appropriate for actually doing the recycling task in the cell. And the second competence we bring is robot learning, especially skill learning, because difficult manipulation task needs to be performed in a cell like this. Then we have an expert in computer vision. So obviously, unlike in manufacturing, where often you can do everything in a feed-forward manner, this is not possible in recycling. So we need to have vision in the loop, and we also need to, and this brings the group of Florentin Vergoter from Göttingen, and they will also contribute to semantic analysis of the task. So, for example, part of the so parts can missing some parts, the workpieces can missing some parts, and then you need to decide to do some manipulation or not. And so the AI technologies here are important. Then in recycling, unlike in assembly, you don't need to be as accurate. You don't need to be as accurate, but you need to be very flexible. So we think that the concepts of soft robotics can help us a lot here, and this is brought into the project by IIT. So the PI is Manuel Catalano from the Antonio Bicchis group, and there's a spin-off of IIT QB Robotics, which brings the hardware into the project. Then, of course, soft manipulation, it can be difficult. So we have experts on robot control in the group of Sami Haradin from TUM. And finally, there's a partner that specializes in, and that is basically bringing the use case into the project, electrocycling from Goslar in Germany. So just a few words about the approach. So we start not unlike how you do in manufacturing. So first you need to develop the solution, how to disassemble the workpieces, and this will be done by programming, by demonstration, kinesthetic teaching, learning, and this will bring us to what we call the archetype solution. So this is basically the basic solution. Then we perform the semantic analysis of this solution, which basically allows us then to decide online which parts of the task needs to be executed for the given workpiece. And finally, we need to be adaptable. So since parts are in different conditions, you need to adapt parameters of your disassembly procedure online, and this is done in this third pillar of the project. So about the impact, well, the industrial impact is obvious because these operations, as you can see here, are indeed done manually at the moment. So if we can partially automate this process, there'll be a large industrial impact. And of course, there is also a positive environmental impact because currently electronic waste is often shipped to the less developed countries where it is where the workforce is cheaper or so sometimes it is just dumped, and so this is of course not good. And we also hope to have different scientific innovations, so like introducing self-reconfigurable hardware and soft robotics in the recycling domain. And we hope to develop new sensory motor learning and AI methodologies to interactively learn the disassembly task for recycling, and finally the new methodologies for automatic reconfiguration online to adapt to different workpieces that come into the system. Thank you.
So thank you very much to all the presenters. So now we go back to the timeline. So this one was the next ICT call specialized on the application areas, and it was in inspection and maintenance. So we had some innovation actions that got like 28 million euros. And there were chosen 3 different projects, piloting, Atlantis, and Buck, right? So now we was just going the first one. So I'm going to introduce.
Thank you. Okay, so I'm going to present the piloting project. This is a project that just started. We have here the consortium. The interesting thing of piloting consortium is that covers the full value chain in the inspection and maintenance sector. Okay, we have 3 infrastructure-related companies: Chevron from the oil and gas sector, and then we have Ferrovial and Natian from the civil sector regarding viaducts and tunnels. Then we have 2 leading technological companies, General Electric Inspection Robotics and Honeywell. And then also we have a number of specialized SMEs, okay, innovation centers, regarding also artificial intelligence and data processing and IoT. And then we have different technological centers like Sintef and also USEF CATED, that we are the coordinator of the project, and 2 universities with a track record in robotics, such as University of Seville and ETH Zurich. So the main objectives of piloting is to move forward into the robotic technology developing in order to achieve TR7. We would like to test these technologies and adapt them in real scenarios. Okay, we will perform 3 main trials or pilots in refineries, in oil and gas, refineries, tunnels, and viaducts. We also like to develop what we call the piloting inspection and maintenance platform that will be open and scalable, and it will include not just the robotic platform, but also all the data processing and artificial intelligence in order to develop a complete solution. So we can deliver to the end users a complete solution that can solve the inspection and maintenance problems. We're going to cover around 8 or 9 use cases, different use cases, and the idea is to generalize this platform that we can use with different robotic platforms and as well to different use cases. Well, as I said before, we would like to also integrate not only the technology partners, but also the end users in the process. So we are sure that our developments are aligned with their interests, and we can truly, at the end of the project, develop a solution that is useful for them. Okay? There are a number of barriers, like, for example, certification, ATEX certification in refineries, and also, for example, the use of aerial robots in windy conditions, things like that we are going to cover specifically during the project. And also, we would like, with the collaboration with other projects in inspection and maintenance in Europe, in order to promote the use of robotic solutions for the inspection and maintenance sector. I think we think really that it's a sector that can grow a lot and can show the potential of robotics. Regarding the approach, it's important that since we would like to have this TL7 at the end of the project, we have organized the project in 2 phases. The first phase will be a first iteration of the project, we will adapt the platform. We will develop a first version of the piloting inspection maintenance platform as well, and the robotics vehicles, and we will go to the sites. So we will have a first experience on the real sites, and with all that experience, we will have a second phase of the last 16 months that we will improve this system, and also with that experience, we will be able, hopefully, to better understand their needs and adapt the solution to the real needs of the end users. Okay, and as I said before, our objective is to demonstrate in operational scenario the different robotic systems that can be used to solve and to make more efficient inspection and maintenance tasks with the end users. Regarding the impact, we really think that a piloting project will make a difference. We think that robotic solution can improve productivity, quality, and safety. Okay, there are the three main aspects that can be improved with robotic solution in the inspection and maintenance. It's important to take into account that in the current situation, the inspection and maintenance tasks are going to be increased, you know, because they are not going to renew the infrastructure. They're getting older and older. It's important to make these inspections much more efficient. And we think that with robotic solution, we can improve this productivity level and also the quality of the data, which is an important part. And of course, as I said before, the safety of the operators, so they don't have to work ahead or go to dangerous situations. Okay? Just to conclude, if you are interested to know about the project and to keep it updated, please join the piloting user group. You just need to send email to this address, and we will incorporate in the piloting user group, and you will keep it updated about all developments and how we are progressing during the next 4 years. Okay. Thank you very much.
Well, thank you. Thank you so much for your presence here. My name is André Pinto. I am the project coordinator of the Atlantis. Here at the Atlantis, our vision is that robotics will be integrated, managed, and operated in the offshore wind farms in the next 10 years. Why? Because they have a lot of potential to reduce the levelized cost of the energy by mitigating the use of supporting vessels, divers, and other type of experts that are required in the field. So, the offshore energy production is expected to be one of the major source of energy in Europe, with future farms being installed further away from the coast at deeper locations. This economic sector is being driven by economic pressures related to the inspection, maintenance, and repair of the assets that are being installed at sea. This increases significantly the levelized cost of the energy, and our idea in Atlantis is to convince the stakeholders about the advantages of using the robotic-based solutions. We will discuss with end users, we will talk with stakeholders about a way to integrate the value of the robotic solutions into their value chains. For that, the Atlantis project rises from this emergent sector, the technological needs of this emergent sector, as well as the research and development excellency that already exists in Europe. We combined several initiatives, some of them led by the industry, others led by the more academic partners, but the interest here is that we put them all together in a way to understand the limitations, the current market limitations, as well as to provide all the required procedures in order to facilitate the rollout of technology, robotic-based technology, to the end users. The consortium is formed by 10 partners from 6 countries. The beauty here is that we have the entire value chain of the robotics and ICT sector, as well as the offshore wind energy sector. Our main goals is, of course, to develop the first European test site focused on and devoted to validation, demonstration of robotic-based solutions in a real offshore wind farm. Okay, we will try to accelerate the development of existing solutions in order to facilitate them to achieve the technological maturity that is required, as well as we will foster the integration of the robotics into the value chains. What is the Atlantis Test Center? The Atlantis Test Center will be a large infrastructure in Europe. It will be installed in Viana do Castelo. Why? Because one wind float, one offshore wind farm will be also installed there. But the interest here is that it will have two locations, one coastal test bed and the other the offshore test bed. As I already mentioned, the offshore test bed will be used for full-scale and realistic demonstrations on a real offshore wind farm. So, this image captures the entire initiative of the Atlantis. We will foster the enhancement of existing solutions, making them more suitable for and prepare it to solve real limitations of the industry. We will deploy the Atlantis Test Center that is formed by two locations, one both in Viana do Castelo. The first, the coastal test bed, will be for de-risking the technology before testing that technology in a real scale offshore wind farm using supporting vessels, of course, in order to supervise these demonstrations. Finally, we will discuss with end users a better way to integrate the value of the robotics into their value chains, as well as to consider all the legal and regulatory limitations that the industry has at this moment. Okay? For more information, be free to contact me. I will be prepared to reply any solicitations. Okay. Once again, thank you so much for your presence and for being here. Okay. So.
Okay, so I'm presenting BugRight. So BugRight is a project focused on the inspection of the outer hull of ship hulls and storage tanks as well. So it's a project which has quite a few partners. We try to get all the value chain of this industry. We have a strong part on academia here, but we try to cover not only the technological skills, but also legal aspect and the psychology of the inspection system. We have some robot providers. We have some service providers which are servicing ships, shipyards and harbors inside the consortium. Asset owners, so people operating big freighters for like shipping stuff around the world. And one representative of the classification societies which are actually holding the regulation process inside this domain. The goal here is to have, to build autonomous multi-robot system that can work on and around a ship hull. So on would be magnetic crawlers, around would be either flyers or underwater systems. And we have two main tasks, which are inspection, so thickness measurement, for instance, but also visual inspection, and cleaning. And cleaning has a very strong economic and environmental impact. I will come back to that later. We will integrate all that into immersive decision support system. And the goal, because it's a pilot operation, we are going to deploy all of this technology inside harbors, at service providers, and shipyards. In principle, it's it's an innovation action, so we basically integrate components which are we mostly know how to do. So we have a process which is quite similar to what you need for this type of task. We'll have multi-robot systems that start from a model of the ship or structure to be inspected, spread that into multiple robots, then get the robots to move around the structure and do the stuff. Collect all the data into the immersive user interface, and then from this data, take a decision on what to do and guide maintenance and integrate that into a decision support system. Because it's, well, we want to get to quite high trial very fast. We have a very strict timeline. I hope I will be able to hold that. Kind of depends not only on me, but we'll have first part of the project redeploying existing system inside the service providers so that they can like localize a system, get data, and get used to the systems. And then from the second half of the project, we'll be deploying autonomous systems on these big assets. In terms of impact, well, obviously from the academic world, which we want to demonstrate this technology for multi-robot deployment and in a large-scale system. Now, on the economical side, in particular, cleaning has a very, very strong impact. Some literature are showing that if you take a tanker with a clean hull or with a dirty hull and just go across the Atlantic and back, you can save of the order of 1 million liters of fuel, which is of the order of 600 to 800,000 euros just by cleaning the hull. And it's done very often, but right now it's a process that costs of the order of 250,000 euros. So it's something which is still quite an expensive thing to solve. One of the challenges with shipping, in particular, is that everything is decided at the worldwide level with UN structure, which is called the World Maritime Organization. So we have in the consortium a direct access with our legal specialists inside this structure. And in terms of environment, well, obviously, if we get a better inspection system, faster inspection system, where there can be more inspection and the ship can be safer, but also if we can solve really this cleaning problem, we'll have well, more fuel-efficient ships. But also, if we talk with the ship manufacturers, if we can really see cleaning as a facility that is happening very often, then you can also remove the need for antifouling. Hopefully, if we can hope to dream a bit. And antifouling is, by design, a very toxic substance. So if we can remove that from this industry, that can have a very strong ecological impact. And that's all I wanted to say. We'll be waiting for you on my poster.
Okay, so now it's time to move to the next timeline. That was on the 20th of March, and the ICT call on competitions in the support action. So in this one of 2 million, we had only one project, Metrics, which I have to congratulate because I was, before moving to Robotics, involved in this one. Yeah. So I will just...
Just too bad. Thank you very much. Hello, everybody. I'm Guillaume Avrin, coordinator of this Metrics project. I'm also head of the department that is doing AI testing at LNE. And so I'm very happy to be here today to present you this Metrics competition. The Metrics consortium brings together 17 partners across Europe. They have a huge experience in organizing AI and robotics competition at the European level. They also have a large connection with digital innovation hubs and cluster in AI and in robotics. And the reason why we need these networks, we need this experience in organizing robotics competition is because the main goal of the Metrics project is to create a sustainable European ecosystem around testing, benchmarking AI and robotic systems through competition, and starting with 4 application areas that has been identified as a priority by the European Commission: healthcare, agri-food, inspection and maintenance, and agile production. And so, because we know that competition can be very efficient at fostering innovation in robotics, at increasing the maturity of the systems that are benchmarked. And but there are three conditions for that. The first one is that they need to rely on evaluation tools that are open, that are rigorous, that are metrology grade, such as, for example, qualified testing facilities, and these tools need to continue to be used after the end of the project, after the end of the competitions. They also have to be organized by trusted third parties that has an experience in organizing such evaluation campaigns, and yes, so the metrics project is going to involve end users that can sponsor the competition to make sure that the evaluation tasks that we are considering during the competition are relevant for market needs. And this is the third condition to have efficient competition, is that we need to have evaluation tasks related to problems, well-identified scientific and technological challenges driven by industrial and market needs. And so there will be this end user involved in the project. There will be, of course, techno providers as a participant of the metrics competition, and the general public that is providing the final acceptance for such robotic systems. And so the method that we are using is really simple. There are 3 points. The first one is that we are organizing one evaluation campaign per year. The idea behind that is that we can evaluate the progress of the different robotics solutions that are participating to the competition. The participant can improve their technology between each evaluation campaigns. It's also useful to evaluate the impact of the metrics project, to making sure that we have a real impact on the technology. The second point is that we are organizing both evaluation campaign in a physical testing environment, what we call field competition, and we are organizing evaluation campaign based on testing dataset. It means that we are mobilizing the AI community and the robotics community to satisfy the needs from either manufacturers or equipment manufacturers or integrators. And the data that are going to be used in the cascade competition based on testing dataset are provided by the field competitions. Okay, and the third point is that we are gathering a lot of different kind of testing facilities in order to be able to really characterize the performances of these robotic systems in the 4 application areas. So to conclude, as we said, competition has a huge impact on the maturity of the technologies that are competing during competitions, and so they are getting closer to market. And as they are getting closer to market, we need to develop conformity assessment tools. So in the metrics project, we will make sure that we are transferring the output of this project to standardization committees, to a working group, in order to define certification standards to support the market entry of this robotic system. Because really the final goal of this project is to contribute to matching the offer and the demand in AI and robotic systems in the 4 application areas. So thank you very much for your attention. I would be happy to discuss further about this project. Thank you.
Thank you very much. So we move in the timeline now to the IC10. This one was in research innovation actions in core technologies in 4 different areas: artificial intelligence and cognition, cognitive mechatronics, socially cooperative human-robot interaction, and then model-based design and configuration tools. So in this one, we had 7 different projects, which is Spring, Vacuous, Opendr, Robucher, Rehive, Sophia, and Aerial Core. And I will just now pass the microphone to the next one.
Good morning, everyone. So my name is Xavier Lameda Pineda. I'm affiliated with INRIA, and I'm the coordinator of the SPRING project, which stands for Socially Pertinent Robots in Gerontological Healthcare. So we have a consortium of 8 partners from 6 different countries, 5 academic institutions, 2 industrial partners, and 1 medical partner. And we have different expertise. So we have expertise in sensor processing, let's say computer vision, audio processing, and the fusion of the two. We also have expertise in dialogue modeling and in robot behavior generation. Also in understanding the environment, so this is robot self-localization and human behavior understanding. The medical partner is in charge of validating the technology in a gerontological healthcare facility. And the 2 industrial partners are in charge of robot manufacturing and software integration. And they have expertise on robotics for healthcare. So to understand what we want to do, I would like you to try to imagine what happens when you place a robotic platform, like the one on the left, into an environment that is close to what you see on the right. So on the right, you see the waiting room of a hospital, and you also see like a social gathering, whatever, like a cocktail party scenario. So the problem is that if the robot has to discuss with people in this environment, it's going to be very tough with current technology. So what we want to do here is to develop, social assistive robots that have the capacity to perform multi-person situated interactions. And this means that the conversations can discuss about many different topics, but they also have to be anchored in the physical environment of the robot. So the robot needs to know, if someone is looking for a chair, needs to point to the empty chair, or if someone wants to get a nurse or wants to get a magazine on the table, needs to understand where is this magazine to grab it. Okay? So our approach builds on these 6, let's say, methodological bricks on the left. The first one is perhaps the most important and most challenging, is the automatic analysis of the robot acceptance. So we want to have a robot that is able to understand if the person that is interacting with is accepting the interaction, is basically not willing to interact. And for this, we need many other things. We need a robot to be able to learn how to take action and to choose the actions, let's say, wisely. We need to have a robust description of the interaction with multiple persons to be able to handle a discussion with multiple persons, of course. And we also need to know what's around, so what kind of objects and where they are, and basically where the robot is as well, right? So all these methodological bricks will be implemented in various software modules that will be integrated in a holistic software architecture. And together with the hardware, that will make the overall system that has to be validated in an elder care hospital. So in terms of impact, of course, the first maybe and most important one is to develop new core robotic technologies, and specifically related to artificial intelligence when it is used for social interaction with the use case of gerontological healthcare. And this use case, it is important because we want to measure the benefit of such technology in this kind of facilities. Of course, we want to push the scientific state of the art in various disciplines, computer vision, learning, interaction. We hope to contribute to the future of social robotics by enabling a robot that is able to discuss with multiple persons at the same time. This is quite novel. And then finally, this is a bit more like midterm. We would like to improve the healthcare experience both for the users, meaning patients and accompanying persons, and for the medical personnel. And finally, we hope to be able to make recommendations for national and regional policies when it comes to use social robots for gerontological healthcare. Thank you, and I will be in my poster if you have more questions.
Okay, hello. This is a short introduction on Vacuous. This is a project for developing mobile robotic platforms for active inspection and harvesting in agricultural areas. It is led by the Aristotle University of Thessaloniki from Greece, with expertise in robot control, robotic manipulation, and remote sensing spectroscopy. Other partners include CERT from Greece, with expertise in computer-cognitive vision and agricultural management. Robotnik from Spain is our partner with expertise in customizing and developing mobile platforms for various robotic applications. And also Saga Robotics from Norway, with expertise in mobile platforms for agricultural applications. The University of Lincoln from England is bringing in their expertise in localization and planning in agricultural areas. And finally, our two end users is Ktima Gerovasiliou. This is a wine producer of Greece, and the University of Torino with the Department of Agriculture bringing in their expertise in growing grapes and vineyards. Now, our ambition is to provide an autonomous robotic ecosystem utilizing mobile platforms and manipulators for intelligent inspection and harvesting and selective harvesting of high-value crops. Now, for this, we have to meet a series of objectives. These are to develop autonomous mobile platforms to explore the agricultural area and assess the crops with respect to their ripeness, health, quality, etc. We have to develop a bimanual robotic platform capable to harvest the crops in a human-like manner. And this should be done selectively. That means by assessing individually each item to be harvested or not. This also, of course, involves intelligence and AI behind. We have also to develop an integrated grass planning framework and optimized grippers utilizing additive manufacturing so that we are able to develop our system in different harvesting applications. And then we're going to develop a decision support system and mechanism for optimizing the operational capacity, the automated operation planning, and the task scheduling and the task scheduling of agricultural operations, and this should include, of course, automatic rapid reconfiguration between inspection and harvesting. Last, we have to enable an autonomous navigation and interaction with the environment in a safe way, and finally to validate the Vacuous platform in real-life scenarios in vineyards. Now, our approach includes developing two mobile platforms. The one is going to be for inspection. This will be enhanced with sensors such as RGBD and hyperspectral cameras and LIDARs in order to perform the inspection of crops like wine and table grapes. And this, as I said before, would be done either for ripeness and health. And also a harvesting robot, and this will be a mobile dual-arm robot with advanced cognitive capabilities for selective harvesting of high-value crops, such as the grapes that we're going to use as our use case in a human-like manner. And this is the reason why we wanted the bimanual solution, and also not only to develop a solution that would automate what human labor does in such cases, but also to enhance it in terms of the way the selection of the grapes are done. Because what is done now is usually they are developing some prediction models and decide on which part of the year they will harvest, let's say, the grapes. And then this is done by hiring temporary labor and do it all over without selecting particular grapes that they have the right sugar content on, and polyphenols that the wine quality is based on, for example. And also this is true for the table grapes. Our use cases will include robot harvesting of wine and table grapes, and these type of vineyards are very different, and the type of grapes are very different in this sense, so these are challenges of harvesting. It will also do yield prediction in vineyards, and the other two use cases concern the thinning of small grapes so that you increase the quality that you get from the rest of the grapes, and also detect any infected wine grapes and remove them in previous stages before the harvesting. The impact of the project is to advance beyond the current state the core technologies of cognitive mechatronics and intelligence in agricultural robotics, and especially with the advancement of bimanual manipulation and safety of reaching the items of interest to be harvested and navigating in this environment with safety. We are going to introduce services supporting the agricultural management and automate tasks like crops quality inspection and selective harvesting in order to allow substantial improvements on the performance of contemporary farming operations. And of course, to lower the technical barriers of the agricultural sector and drive user acceptance, and thus boost agricultural and robotic leadership for future growth, sustainability, and global competitiveness. Finally, of course, an automated solution reduces manual labor, and this addresses also the issue of human labor shortage, particularly if this labor is temporary in the area of agriculture. So that's all for me, and if you are interested in this project, you can visit our webpage and social media, and we'll also be outside with a poster, and I have some brochures if someone wants to have a look. Thank you very much.
Hello, so I'm Anastasios Stefas, and I'm coordinating the project Opendr, which is, I'm from Aristotle University of Thessaloniki. It comprises of 8 partners. We have Tampere University and Aarhus University, and TU Delft and Uni of Freiburg, and 3 industrial partners, Cyberbotics, PAL Robotics, and AgroIntelli. In total, we are 4 robotics groups and 3 machine learning groups and 3 industrial partners. So what is Opendr? Opendr is an open deep learning toolkit for robotics. And the idea is that we want to provide an open, non-proprietary toolkit that will be easy to train and deploy for all that are trying to use robotics in their applications. We have certain barriers like the steep learning curve, and our approach is to provide a modular and easy to use deep learning toolkit for this. We have the barrier of computational complexity. Many of the results we've seen nowadays are based on huge GPUs that cannot be used in robotics, especially on board, for example, in aerial robotics. So our approach would be to provide lightweight models that are specific for specific applications to be able to run in real time in specific GPUs like Xavier or TX2. And also, we are also aiming to go from static perception, which is what we can usually see in computer vision, let's say, conferences, to active perceptions in the second version of the project, where we can indeed exploit the robot that we have in hand in order to be more efficient and have better performance in our tasks. So, in our approach, we have actually a collection of tools that we can use like PyTorch, TensorFlow, these frameworks that are used for deep learning. And we are aiming to provide ROS-compliant, of course, tools for, and ROS2, we're discussing inside the consortium also big ROS2 compliant. And of course, this can be a co-integration with the simulation environment. So of Webots, since we have Cyberbotics as a partner. So we will provide real-time inference on high-resolution data, which is very important. And we have selected 3 challenging use cases to demonstrate the usefulness of this new toolkit. These are agricultural robotics from AgroIntelli, healthcare robotics from PAL Robotics, and also agile production, which will be in the University of Tampere. So the first release of the toolkit will be on month 18, and the second one on the end of the project where we have the full functionality, let's say, of what we have in mind. Regarding the expected impact, of course, we want to improve the technical capabilities in robotics by providing easily deployable tools. So we want to help the robotics community, since some of us were coming from the machine learning, let's say, community. And in order to enable, of course, a greater range of applications, and we will focus, of course, on the specific use cases, but we are open in any other use case that will give us feedback and requirements, because we want this toolkit essentially to be rather generic. And with this, we hope that we will strengthen the competitiveness of companies by giving them access to, let's say, efficient deep learning tools. You can learn more about OpenDR by visiting our website and also on following us in social media. So thanks again for being here, and I will be in the poster session.
Yeah, so my name is Alex Mason. I'm here to talk about the Robucher project. So this is a project which is targeted at the meat sector. And it's actually targeting a challenge that faces the meat sector in regard to labor shortage and the poor accessibility that they have to automation. Of course, it is possible to find automation in the meat sector. And in this project, we target the slaughterhouses, where actually automation is the least accessible. We were talking with some colleagues in Spain, some end users in the project, and there are examples in Europe where you have automation that can handle hundreds of thousands of animals per day. But the problem is that they're only reproducible across several places in Europe. And there are thousands of producers. And those thousands of producers, what is their option? Lots of people working manually on slaughter lines. And that is a big challenge. One, because finding people to do that is difficult. And two, because, of course, that environment is quite dangerous. There are sharp knives, there are heavy objects. And that makes life difficult for the workers. So in the Robucher Project, what we have, I'm from NMBU in Norway. And we have been actually leading a few national level projects to develop a concept that moves away from the traditional line process that exists in slaughterhouses today. But we also brought in an expertise across Europe. So we have more from academic circles, so those that are, for example, above the university, who are from Hungary, who are dealing with more medical robotics, but that helps us a little when it comes to handling flexible and difficult materials. Doing so without damaging it. And also we have a lot of representatives from Norway, from Denmark, and from Germany, Animalia, DMRI, and MRI, who have kind of meat sector knowledge from the end user and also the consumer perspective. We also have robotics integrators, Robot Norge, for example, who supply ABB robots and integrate them into the market. As well as expertise in artificial intelligence from Cyclum in Ukraine. And of course, I said we are talking with end users in Spain, and we actually have an end user, Faxa, who is involved in the project. But the meat industry is really interested in this project, so we actually have quite a few that are following the project as well. So we have an end-user reference group, which at the moment consists of 5 or 6. We started in January. That consists of 5 or 6 additional parties that follow the project purely out of interest of their own cost. And we hope that will continue to go on. So in terms of the mission of the project, what we actually try to achieve, well, of course, we have the buzzwords from the call. It's very easy to reproduce those. But what we're trying to do here is we have a challenge when it comes to dealing with animals, right? We have a highly flexible and highly variable material to work with. So we have to improve and work with the artificial intelligence systems to be able to cope with that. So that we can, what we're trying to do is we're trying to cut, right? That's what an abattoir is all about. So we need to be able to improve those artificial intelligence systems to be able to adapt and understand what is presented and provide reproducible activity. It's not all about artificial intelligence, though. We also need gripping and intelligent tools that can keep up with the AI systems. So we need to be able to interact with the carcasses and with the material while it's still hot. And that means we have to have appropriate tools to be able to do it, to understand, to give feedback that is along the line of what a butcher would be able to feel and experience today. So we've got a big challenge when it comes to those sorts of things. And of course, we actually started this project as a cooperative robotics project in Norway. And what we soon realized is we're working with material that's 120 kilos and we're breaking it down. We're a disassembly process. And the problem with the legislation in robotics is that we can't really have collaborative robots working when we have such heavy lifting and weights and so on. So here we have been looking at, of course, full automation. But we also consider the fact that the AI systems may struggle and we need some ability to adapt and to interact and so on. So we're also looking at how we can integrate teleoperation into these sorts of systems. When we say this to butchers, can we butcher with an Xbox controller? They sound quite excited about this sort of thing. In terms of approach, we've actually been building a cell in Norway. Here we've got a simulation view in Robot Studio, but we actually have this system being built in our lab at the moment. So we have at the moment one ABB IRB 4600 robot, and we're probably going to get another one in about a month. We also have been concentrating on building, we have quite a large, we call it a carcass handling unit, but it's basically a big hand that can handle 120 kilos. And it can present it in more or less every direction that you need to be able to cut and manipulate a carcass. So what we are trying to do here is we have this platform. It is in Norway. It exists. We are trying to then build in the competence of others around Europe. So from the artificial intelligence and trajectory planning perspective, this is where we have competence from the Ukraine. When it comes to gripping and manipulating, we have competence from DMRI, Danish Meat Research Institute in Denmark, and also a Bodø University with a background in medical robotics. And then we also have intelligent cutting tools, so understanding how the tools actually function in respect of the material. And eventually what we plan to do is we plan to ship the whole thing to Germany and actually have a competition with an existing line. So we'll actually see how it performs alongside an existing traditional disassembly line. So to end, what do we try to do? We try to make a system which is robust, flexible, and scalable. Yeah? So that it can tolerate some failure, which lines can't do today, so that it can be flexible for different levels of input. Having 110,000 pigs per day go into one plant, that's a difficult thing to do. And that is 2 weeks of production in Norway, right? So you need to be able to scale production. And when it comes to scalability, you need to be able to figure out how you can increase the level of productivity in the meat sector. And we need to do this regardless of production volume to cope with the variety of production that go on across Europe. So if you want more information, we'll be at our poster, and you can also go to our website, robucher.eu. Thank you very much.
Thank you.
Do you have a pointer?
It's okay. Okay, thank you very much. So I'll be presenting a project called Rehab, that's short for rehabilitation based on hybrid neuroprosthetics. That's basically rehabilitation for stroke patients. For the consortium, we have 11 partners. So TUM, Technical University Munich, is coordinating this project. We also have 3 hardware developers. One is UVO, and then SSSA, and also Technalia, who is actually developing this technique called functional electric stimulation. Also, OZO is looking at exploitation side of our device development, and also the IBEC and the Technical University of Denmark are looking at this cognitive architecture for designing like patient-centered rehabilitation device. And also we have a couple of clinical sites, Schirm Clinic in Germany, also Valduce in Italy, basically doing patient testing and evaluation and giving some opinions about the device development. And also we have Stella from Germany looking at the legal side of the projects. So the ambition of the project is really making this exoskeleton device that's usable for the patient at home. And our exoskeleton is on top of classical exoskeleton techniques. We introduced this technique called functional electric stimulation, and that's a technique used in clinical practice for assisting patients by directly executing electricity into the muscles, so we can actually have the patient using their muscle activities move their movement. The problem there is that the muscles are very stochastic and hard to control. So we need to really understand exactly how the muscles are being used and also combine that with the exoskeleton. And in the result, what we can do is like functional electrical stimulation. It's a very small device. So we can reduce the overall size of the exoskeleton, and we can make the device usable, for example, at home, as well as in clinic for various situations. And what we'd like to do is like using this device for various rehabilitation routines that are currently done by physiotherapists, using in time-consuming manner, but with the exoskeleton we can do it very repetitively quickly, but also we can do some exercises at home while monitoring patient behavior using sensing devices. And our research focus is mainly really focusing on this like monitoring side of the patient. So what we call this technique called digital user twin. So we could try to create in silico representation of the users, so we can actually monitor how the patients are working in some kind of training programs and what kind of motion that they're executing in daily life. For example, some movement may be like not really favored by patient and being avoided, so we need to really advise the training program to make sure the patients are doing a whole range of motions that's necessary. So for the approach, like I said, we have this participatory design from clinical users that's heavily guiding our research program. So what we have is like all the questionnaires and user testing done by the clinicians with patients and the other clinicians about the opinions that would be reflected in development of exoskeleton and functional electric stimulations. And what we do is trying to use that knowledge into creating digital user twin, that's representation of the users, and then trying to find a way to control optimally for using both of these techniques at the same time, so it fits to the right use case and user requirements, and employing that into clinical and home environments for various applications, including ADL assistance, serious gaming, and general human-robot communication technologies. So for impact, there are multiple impacts, but the main thing that we are aiming for is this rehabilitation device that can be brought to the home environment, and we can do continuous monitoring of the patient, and that's very useful information for clinical intervention, because typically, like when you're actually treating a patient, what happens is that you have intense caring at the hospital, but as soon as they're released from the hospital, the patients are not monitored at all. But using our exoskeleton devices, we can actually monitor what the patient is doing in everyday life. And that's very important information for guiding the clinical interventions. And also we have a multitude of developments. So for example, the communication device between human-robot interaction can be used for any general human-robot interaction setting up, as well as serious gaming that can be used for different patient populations. For example, we can use the same device for with slight modification for assisting Parkinson's disease patients. So there are quite multiple impacts. And if you have more discussions that you would like to, I will be at the poster. Thank you very much.
Okay, good morning everyone. My name is Alasha Giudani. I'm the coordinator of the SOFIA project. I'm from Italian Institute of Technology. SOFIA stands for Socio-Physical Interaction Skills for Cooperative Human-Robot Systems in Agile Production. And our objective is to create highly flexible systems that can actually improve productivity of the production systems. And the reason for that, if you think about it, we've taken collaborative robots, but we're actually using them same as industrial robots, just removing the fences, right? Because we believe that they have higher potential to come in close connection with the humans, not necessarily physically coupled, but be close to them to be able to work with them more productively and for a longer period of time. The second very important thing is we want to improve their ergonomics. Since these systems are very reconfigurable, adaptive, and flexible, they can actually contribute to improving the ergonomics of the people. Numbers are really bad. 240 billion euros every year European Union is spending for musculoskeletal disorders associated to the industry work. It's absenteeism and lost productivity. To create this system, of course, we had to bring this interdisciplinary consortium. On your left side, you see the research partners, which IIT is coordinating the effort, but University of Pisa, University of Montpellier, VUB, Brussels, and University of Twente. I'll explain what you're doing in a bit. In the middle, we have some, we want to look also into the acceptability and standardization potential of the technologies. That's why we have ENAIL and BAWA as governmental organizations for occupational health and safety. And we have DIN for standardization, which is from Germany. And we have use cases to be able to show these things work, actually. So we have Volkswagen, the largest car manufacturing in the world. And we have Hydria, which they are component manufacturers and hand cam gears. So we have the large enterprises, we have and SMEs. We want to show that they're flexible enough to actually demonstrate in within all the use cases. So the entire vision is what we do. So this is probably the current state. We believe that humans are able to adapt to the environment. Robots are somehow able to adapt to the environment as well, but the connection actually is missing the way it should be, the way it should has to demonstrate the potential. So SOFIA project will target those to, first of all, to make sure that humans and robots actually adapt to each other very, let's say, flexibly and adaptively to improve each other's states, like productivity for the robot and ergonomics and working conditions for the human. Robots can also, we want to also push forward the, let's say, adaptation potential of the robots to the environmental changes, because SMEs are not very structured, but we have lots of variations in the production line, so the robots should be able to adapt. For this reason, we are looking at the cognitive mechatronic systems. We will develop mobile manipulators that you can see some examples there. And we will also develop under-actuated, let's say, modular exoskeletons, just focusing on some specific joints that are subject to danger in some use cases. And we will also develop some interfaces to feel the people, basically, both socially and physically. And what it means, basically, we have developed some sort of flow of the work. On the top, of course, we have the observation layer to see how the fatigue progresses, physical and cognitive, of course, and how the musculoskeletal disorders in short to long term has the potential to grow. And then we will anticipate what's the best way of working, then if we can avoid it and we can actually change the way it should be done. We have the perception layer, of course, is on the robot side. It looks at the environment, changes, variations of the product and people and basically within the process. And the robot actually starts blending the shared autonomy layer between human and the robot to allocate the roles in the most productive and ergonomic way possible. For the first time, we want to bring the two concepts of physical and social interaction together, because usually in robotics, if you go to the conferences, we have physical interaction sessions and social interaction sessions. We want to have a framework of unified socio-physical interaction between humans and robots. And of course, we will bring these components in our use cases to show the technologies. The objectives, of course, I'm not going to mention them. Of course, we have technology objectives, we will have use cases, and we want to also bring somehow try to understand if we can create new standards, at least try to modify and understand the standardization potential of the new, let's say, safety and concepts that we will develop within this project. We have a really good group of digital innovation hubs. We are working with, we had a workshop yesterday actually with Trinity for the first time. We are actually working with some unions and companies, as well as, let's say, some other companies which are slightly related to the healthcare, because we want to show the modularity of our approach. So if it's not only useful for the production, but some of the components, for instance, musculoskeletal modeling, can be used for rehabilitation and things like that. So the modularity is at the core of the project. Of course, we want to impact a lot. We want to show that through our use cases that are including SMEs and large enterprises, we want to show that the systems are working. And the impact, apart from the usability and scalability, are basically the social sustainability of the systems, because these systems, as we know, are not meant to replace people. They are just alongside people and make them work in the longer and happier working time. And of course, we want to try and refine some standards for socially and physically cooperative systems. If you have any questions, and if you're interested to know more about the details, I'll be right over there. Thank you very much.
So good morning. This is Aníbal Ollero. I'm coordinator of this aerial core project. I think that this is the only project focused on aerial robotics. We are 15 partners. I think that they have very strong research and innovation capabilities, so mainly all the leaders in this field in Europe. And we also have very innovative companies, small companies also, and large and very committed end user. So I think that we have these ingredients. Now, the idea is to have in aerial robotics cognitive capabilities. So put cognition for what? We want essentially to increase the range, so flight endurance, and also to increase the safety in the interaction with people. And these are also will be applied in inspection of large infrastructure. So particularly, we are considering the combination of long range and also local, very accurate inspection of infrastructures. Additionally, we want to maintain the maintenance. So we want to have maintenance by using aerial manipulation from the results coming from the previous project, AeroArm, that you will see in the next session. And also we want to have safe aerial coworkers. So you can see how even in this work at Hayes, there are different workers at the same time. So we want to help this user also with robots. Then, you can see in this slide how the interaction between the main components. So we have cognition in the center, we have cognitive mechatronics, but also we will apply this cognition for first morphing, what means change the configuration during flight to have more long endurance of the flight, but also being able to hover and also to land, even to land on, let's say, very constrained spaces, like, for example, cables. In addition of this, we will have also the manipulation after, for example, flying or after landing on wires, for example. And we will have also the possibility of interact safely with the people, with the worker, not only visual interaction, but also having possibility of physical interaction. We try to show some concepts in this video. Short video, I hope that it's just to show the concept. So it's preliminary, that was prepared some months ago. So the idea is to, no. So thank you. Go ahead. So the idea is being able to, for example, this illustrate morphing morphing capabilities to fly, to observe, in that case, the electrical line. So it will be able to inspect the line with this strategy. And also, we will be able to interact with people and manipulate. So you will see here, for example, how this is providing a tool to a worker working in the line. But also, you can see here some interaction should be very safe, but also it will be able to have manipulation. So this is manipulation activities when it's pressing on the line. We are analyzing different implications of different manipulation configurations, but also we will have these capabilities. Okay, we can go next. Finally, this slide analyzes the impact. Now the impact. So we want to maintain the position that we think that we have right now at the level of the leadership in aerial robotics in the world, and also the application to inspection and maintenance. So we want to maintain this position with the development in this project, scientific and also technology development. Second, we want also to apply in this huge market with the drone. So look to this number, $127.3 billion. So only infrastructure is $45.2 billion. And also because our validation case, which is electrical power line inspection, that we will have beyond visual line of sight inspection, also manipulation and also co-working. And this has been also analyzed, for example, for the Electrical Power Research Institute that estimates just the losses, outage losses, between 100 billions and 160 billions dollars. So we think that in addition of the scientific and technological leadership of Europe, we will be able to enter in this big market. So I think that if you want to know more details, you can also go not only to the poster, but also to the booth. So we have a booth, even if we just started, we have a booth in the exhibition that you can visit, and obviously we have the poster. So thank you very much for your attendance.
Thank you very much. So then basically we go to the end of the session. I could do 3 things. First, congratulate all the projects that got funded. I'm really looking forward to see how they evolve because they all look very cool. Also, to thank all our speakers here and the people that has come to the workshop. And the third thing I would like to do is to invite you to come to the next workshop later after the coffee break, because we will have some success stories. So we could see like projects that were funded before, how they have really been very successful. And I think this could be great to have you here. So thank you very much, and see you around.